Yes. Sure.
For
Yeah, yeah.
welcoming. Hello. So, good afternoon to all the participants, students, and faculty members. So, I thanks organizing committee, okay, for giving me this opportunity to introduce Professor Raj. So now everyone in the hall is quite familiar and friendly with Professor Raj. So everybody knows him very well, and while I observe the students interacting a lot with him, so he's really enjoying. So I urge all the students to interact as much you can and ask questions. If you have any query, so he will be more than happy to answer all your questions, all your queries. Right? So Professor Raj, so far, I think he has covered all the big spectrum of the nanotechnology, nanomaterials, and their applications, mainly in agriculture, okay, in solar system, in water-related system, how to get drinking water from the ocean, from the sea, and how to use nanomaterials in oil spill treatment. And yesterday he really pointed out how to get good publication and which are the major components that should be incorporated in a research article. Right? So I urge you again and again to interact with him. Right? So he didn't need any formal introduction. Now we have again the same speaker. So I welcome you, sir, again to continue on the same topic.
Yeah.
Thank you.
Thank you. Yeah, please, I'm here for you. You know, I'm going to be here until Friday. If you want to ask me questions formally or informally, no problem. Please feel free. I'm at your service. So we talked about many things. This topic actually is also huge. All this subject of energy storage is naturally a very, very broad field with lots of activity. Nanotechnology is part of it, but obviously we cannot cover it even in 1 year, not in 1 year maybe, but not in 1 hour. But we will try. I'll give some highlights, some stories where nanotechnology can help us in energy storage. So specifically, we will talk about batteries and supercapacitors. These are the two main features or main components of energy storage devices. So we'll talk a little bit about the differences and the common things about batteries and supercapacitors. Then we'll give some specific examples of how nanotechnology can help us with lithium-ion batteries, which are the most common batteries that people use these days. Then we will talk about nanoparticles in electrodes, which are the main parts of the batteries. Then we'll switch to supercapacitors, and we will talk about nanotechnology in supercapacitors, specifically in electrodes, how we're going to make good electrodes for supercapacitors. And finally, I'll tell you another story about something that we done in my laboratory about very interesting light-induced or photo-rechargeable supercapacitors. Now, why do we need energy storage at all? We talked before lunch on solar cells. Now, when we have solar cells and we have energy, we need the energy not necessarily in the same moment. For example, we have sun during the day. What about the night? We need energy during the night. That's why we need energy storage. We need efficient ways to take the energy from solar cells, for example, and store it for later use, for example, at night or in other times. This is why energy storage is at least as important as solar cells for developing new energy solutions for the world. Okay? It's not working, so I will. Okay. Batteries versus supercapacitors. These are two main topics of energy storage. Each one is doing different functions. Batteries are naturally maybe the more important or the more widely used energy storage. What we have in battery, we have two electrodes, negative electrode, thank you, negative electrode and positive electrode. And all what we need to do, we need to have charges in the different electrode. We need negative charges in the positive electrode. We need positive charges in the negative electrodes. If we can hold the charges, we can separate the charges and hold them. That's how we store energy. When we need the energy, we're going to connect the circuit, and the charges will go away. Electrons actually will go from this side to this side, and we have energy, we have voltage. That's how batteries work. The concept is very easy, very simple. Of course, the concept is simple. Doing it sometimes is very challenging. This is batteries. Supercapacitors are working on the same concept, but their role is different. Again, in supercapacitor, we have two electrodes, negative electrode and positive electrode. In both electrodes, we have positive charge in the negative electrode, negative charge in the positive negative charge in the positive electrode. Now, the difference between batteries and supercapacitor is that when we operate the battery, the charges are actually moving from side to side. So the process is quick, and you can have many charges on both electrodes. That's why in energy, you can store a lot of, in battery, you can store a lot of energy. Now, in supercapacitor, what you have are redox reaction, reduction, oxidation reactions in both electrodes. This is why the amount of charge you can store in supercapacitors is lower, but because redox reactions are very fast, you can get very high power in supercapacitors. You can very quickly get a lot of energy. So basically, the main difference between batteries and supercapacitors are the energy. Batteries can store more energy. That's why in all our computer and cell phone, everything, we have batteries, because we want to store as much energy as possible. Supercapacitor cannot store so much energy, but they can give you very high power. They can give you a pulse of energy very quickly. In some applications, it's very important. If you want high energy in short time, for example, when you want to have electrical car and you need a lot of energy to get the engine going, that's why you need a supercapacitor. But supercapacitors cannot store a lot of energy. Anyway, these two systems, they complement each other. We need good batteries for certain applications. We need good supercapacitors for other applications. So let's start with batteries. And let's start with the most common battery that we use in the world these days. It's called the lithium-ion battery. Now, lithium-ion battery, as you see from the name, what we use for charging are lithium ions. Why lithium ions, do you know? Where is lithium in the periodic table? In the beginning, very, very small. It is actually the smallest ion that exists. Lithium has 3 protons, very small ions. Why it's important to have a small ion? Because 2 things. If we have small ions, we can store many, many ions in the electrodes. Small ions, certain volume, we can have many ions. If we can have many ions, we can store a lot of energy, a lot of charge. That's one reason why we like or we want lithium ions. The other reason, because lithium ions are so small, they can move very easily between the cathode and the anode. If they move very easily, it means that we can use the battery very efficiently. We charge the battery efficiently. We use the energy very efficiently because we can use the energy only if the ions will move freely between the 2 electrodes. So this is the main thing about lithium-ion batteries. The challenge in lithium-ion batteries, actually in any battery, is to design the electrode matrix that will be both good at holding the ions. You cannot just have ions going in solution and stick to the electrode. That's not going to be efficient. So we need a good framework for the ions to sit. And we also need the electrode to let the lithium ion move quickly when we connect the electrical circuit. And this is where nanotechnology is very important. Because the contribution of nanotechnology to lithium-ion batteries and other types of batteries is to design good electrodes with good structure, with nanostructures that will keep the lithium ions and let the lithium ions move freely. Okay? Let me just show you, actually, this is related to the previous slide about the difference between supercapacitors and batteries, so let's skip it. Just to summarize the difference between batteries, high energy, batteries, high energy, low power, supercapacitors, low energy, high power. So this is the essential battery module. Let's see how nanomaterials can help us in batteries. Again, we said we want good organization of the electrode, of the nanostructures in the electrodes that will give us good matrix, good electrode. What you see here in the scheme is actually one of the most popular applications of nanomaterials in lithium-ion batteries. What we see here are nanotubes or nanowires that are mixed together, forming the cathode. Now, these nanostructures are very important for several reasons. One thing is, when we have these nanowires or nanotubes in the cathode, we can have many sites for the lithium ions to sit. They can attach to the nanowires and have a stable organization in the cathode. The other thing about these nanowires is that you see there's a lot of empty spaces. There's a lot of pores. Now, why do we need these pores? When we connect the circuit, the lithium ions need to go away and come back to the anode. So we need all these open spaces for mobility of the lithium ions. These are some examples of lithium-ion batteries using nanostructures. In the cathode, we have certain crystalline structures. They can be from many materials. Some popular materials, some nanostructures in the cathodes are polymers or transition metal oxides. Again, all these species are very important in terms of sites, keeping the sites for the lithium and letting the lithium move back and forth. Now, in the anode, you need different organization. You need an organization that will be both porous, but you need it to be also conductive. You need to have electrons going from the lithium metal to the electrode and closing the circuit. This is something you don't need in the cathode. In the cathode, you just need a nanostructure to have sites for the lithium ions to sit. But you don't care about conductivity. The electrons for the lithium will come from here to the electrode. So one thing about nanostructures in the anode is they need to be conductive. Now, there is a very good material that can be conductive. You know what it is? It's written there. Carbon. Carbon, which we talked about a lot, is both good for us, but it's also conductive if you make it in the right way. Remember yesterday we talked about graphene. The graphene sheets, they are excellent conductors. There are other, graphite is also very good conductor. So in the anode, in many batteries, we have organization of carbon nanostructures, again, that will give us a lot of surface area, also conductivity. Here we just have, there's thousands examples in papers about nanostructures in lithium-ion batteries. Okay? People are always trying to make new materials, improving the energy density, improving the conductivity. This is a very, very active field because lithium-ion batteries are so important. So here you see some example. People made this composite material in the cathode, lithium, iron, phosphate. And then in the anode, we have these carbon structures. Again, many, many different designs. But what I hope I showed you is what is the purpose of these designs, these nanostructure designs in lithium-ion batteries. Okay? And again, we talked about graphene. Graphene is very good and very important in lithium-ion batteries. I think actually there are commercial lithium-ion batteries with graphene. Now, you can have also nanoparticles as part of the battery electrodes. This is just an example of an interesting cathode material made of tin dioxide nanoparticles. Okay? So they show you here how they make the electrode. They start with some big particle. They do some chemical process. But what is important is this. It's interconnected tin oxide nanoparticles. Again, why we like it? It gives us a lot of surface area, so we can put the lithium ions in many places inside the electrode. It also gives us these spaces here, which gives mobility to the lithium ions. So this is nice electrode. This is the battery world. Again, what I gave you is very little insight about nanotechnologies in batteries. There are thousands of examples of nanostructures and nanotechnologies in the battery research. If any of you would like to work on that, obviously you need to search in the literature because it's an extremely active field. So, we talked about battery. Let's talk about supercapacitors. Remember, supercapacitors, more power, less energy. This is just an example of the concept of supercapacitor operation. Again, we have two electrodes. We have the charges inside the capacitor, just moving around. When we charge the supercapacitor, when we connect it, we see that the charges go on both sides. They are organized. Negative charges on the cathode, positive charges on the anode. That's when the supercapacitor is charged. Then we want to use the supercapacitor, so we connect it through a load, and the supercapacitor can give us energy very quickly. Okay, and the electrolyte or the charges going back to the electrolyte. Actually, when we look closely on the supercapacitor component, again, it's very simple electrochemistry. This is the cathode, the positive electrode. This is the negative electrode, the anode. And in the middle, you have the electrolytes. Now, the electrolyte is very important because the electrolyte are the charges that go between the electrode and give us energy and give us power. Now, in this picture here, you see the most important part of the supercapacitor and why we need nanotechnology. If you look at the electrodes, they're very porous. We need a lot of surface area in the supercapacitor because what will determine the power and the effectiveness of supercapacitor is how many charges you can put on the two electrodes. if you can put a lot of charges, you can have high power. That's what's important about supercapacitors. So the requirement in the supercapacitor world is to have high concentrations of charges on the cathode and on the anode. If you have a porous electrode, then you can put a lot of ions because you have very high surface area. So if you need porous electrodes, nanotechnology can really help you, because nanostructures can give you a lot of surface area. Actually, there are two types of supercapacitors. Both of them require very high surface area. One mechanism of supercapacitors is just accumulating charges on the anode and the cathode. Again, we need a high surface area for the charges to accumulate. Another very interesting mechanism in supercapacitors is called pseudocapacitance, and we have redox reactions on both electrodes. Again, in both cases, we need high surface area. So also in the supercapacitor world, if you open papers, there are thousands of papers of people making very intelligent designs for the electrodes that will give us high porosity and high surface area. Here, just few examples. Some people put just activated carbon, regular surface area. Other people put holes. You can have holes in the anode and the cathode. By putting holes, you can have the charges accumulate on both sides of the electrodes. The sizes of the holes are nanostructured, nanoscales, to let only ions go in and out. And then, of course, you have various designs of nanostructures to give us high surface area. Again, you have beautiful studies, beautiful pictures. You can see here just an example of some composite material from nickel, cobalt, carbon, whatever. You can build nano towers. You have nano channels, nano sheets, nano cones, everything nano, as long as you give very good surface area for the charge to be stored. Now let me finish with a story, an interesting story about photo-rechargeable supercapacitors. Basically what we're trying to do here, we were trying to make a supercapacitor that we can charge with light. Now, why do we want to charge supercapacitor with light? Why is it good for us? Ideas. Is light good, bad, cheap, expensive? How cheap? Does light cost us money? Environmental, that's right. How much light cost us? $0, 0 rupees. Why? Go outside, the sun is free, it's still free. Maybe the government will charge us for the sun, but light is free. So if we make supercapacitor or a battery or whatever, we put it on the roof, okay? And then there's sun, there's light coming, and we can charge the supercapacitor with the sun. This is going to be great. It's not going to cost us anything to charge the supercapacitor. You know, if you have a cell phone or computer or whatever, You need to put it in electricity, you need to charge it, it costs you money, okay? It's not such a high cost. But think about a giant supercapacitor that you want to have air conditioned for this entire building. It takes a lot of energy. So if you have some supercapacitor or a battery that can be charged with light, with the sun, that's going to be extremely useful. So that's the idea. To make a photo-rechargeable, light-rechargeable supercapacitor. Now, things like that already exist. People made photo-rechargeable supercapacitors. The way they make them usually, there are two ways. You can make a supercapacitor that the electrodes will be light sensitive. So when you shine light on the electrode, you're going to have some chemical reaction that will give us the space, the charging of the ions. This is okay, but it's very difficult. It's very difficult to make electrodes. It's chemically difficult to make electrodes that will have some chemical reactions that are triggered by light. This is why these things, you don't find them in the store. They're not practical because it's difficult to make. In our system, we use a different concept. What we used are electrolytes that are going to be light sensitive. So instead of making a very complicated electrode with complicated chemistry that's going to be charged by light, we'll do something totally different. We will make electrolytes that are going to be charged by light. And for now, you know that I really like carbon dots. So the electrolyte that we used are carbon dots. And let's see how it works. You saw this picture 10 times already. One reason why we like carbon dots, because it's very cheap, etc., etc. We can make it very easily. We don't need to be a sophisticated chemist to do that. We saw this one also, the color properties of carbon dots. And we saw this also already. This is also going to play a role in this system that I will describe to you now. Specifically, this, the photothermal effect of carbon dots. How does it work? This is our photo-rechargeable supercapacitor. What we have, 2 electrodes, standard electrodes, nothing complicated. You know, in every supercapacitor you need to have electrode. Here, this is the electrolyte. Now the electrolyte that we used are carbon dots. But the carbon dots in this case are sitting inside a polymer. So it's a solid material, a polymer called polynipam. Now, polynipam, this is just the electrode. It's a standard electrode that we make with nickel and ruthenium. And the electrolyte, the carbon dots sitting in this polymer called polynipam. Now, polynipam is a very interesting polymer. It is a heat-sensitive or temperature-sensitive polymer. And what I mean by that, in low temperature, the polymer chains are extended, and the polymer is hydrophilic. The surface here is hydrophilic, it attracts water. Above a certain temperature, which is actually about 32 degrees, the polymer changes its phase. It undergoes a phase transition, and these chains are getting entangled, and the polymer becomes hydrophobic. So we have a hydrophobic phase transition induced by temperature. What does it have to do with supercapacitors and carbon dots and all this story? This is the interesting part. In high temperature, the polymer, in low temperature. In low temperature, the polymer is hydrophilic. Now, if we put inside the polymer carbon dots, hydrophilic carbon dots, charged carbon dots, in low temperature, the polymer is hydrophilic, so the carbon dots will sit on the polymer. They'll stick to the polymer because the carbon dots are also hydrophilic, they are charged. Now, when we shine light, what will happen to the carbon dots? You should know this by now. They generate heat. The photothermal effect of the carbon dots. The carbon dots going to absorb light, release heat. They will release heat to the environment. What will happen to the polymer? The temperature of the polymer will go higher and higher until the polymer will do a phase transition. The polymer will become hydrophobic. Now, if the polymer becomes hydrophobic, what will happen to the carbon dots? The carbon dots initially here, they sit on the polymer. But at higher temperature, we have hydrophobic polymer. The carbon dots don't feel good anymore. They cannot attach to the polymer. The polymer is hydrophobic. The carbon dots are hydrophilic. They are charged. So the polymer will need to go to the solution. They will have to leave the comfortable home of the polymer. If the carbon dots are in the solution, they will be an excellent electrolyte for the supercapacitor. And then the carbon dots can give us energy. The carbon dots can be used to charge the supercapacitor. And this is the concept that we have here. In the dark, at night, the polymer is hydrophilic, the carbon dots sitting here, nothing happened. No electrolyte in the supercapacitor. The supercapacitor cannot charge, cannot give us energy. Nothing happens. But when we shine light on the supercapacitor, when there's sun shining, then the carbon dots absorb light, release heat. Release heat, the temperature of the polymer goes up. The carbon dots get released. They can go anywhere they like, and we have an electrolyte to give us energy. This is the concept, just to show you that it really works. See, this is the simple test tube, plastic tube. Okay? We put two electrodes here. Here, this is the polymer without carbon dots. Here, we see the polymer with carbon dots. Carbon dots are brown, so we see a brown color. Now, we shine light. Initially, nothing happens. 2 minutes, the temperature goes up. And you see that the polymer becomes kind of cloudy because the polymer becomes hydrophobic. We shine more light, 4 minutes, the temperature starts going up here, 26 degrees, more cloudy. 8 minutes, higher temperature. You see it's even more cloudy here. 34 degrees, at 10 minutes we get 34 degrees. And this is total phase transition. We even don't see the carbon dots because the polymer becomes like a gel, very cloudy. This is how we perform the experiments. Here you see the energy, the capacitance of the capacitor. So just by having carbon dots, we get a very high capacitance. And what you see here is a cycling. We can charge and discharge the capacitor many, many times just by shining light. Okay, so we shine light, high energy. We charge the capacitor. We turn off the light, low capacity, high, low. This supercapacitor can be used 1,000 times just by shining light. And just to show you that this is actually working, see, first we shine light, we charge the supercapacitor, and now we disconnect it, okay? No, we don't, we connect it to the lamp here. You see an LED. Let's see. It's working. We charge the lamp just by the supercapacitor. And it will go for a few minutes, which is what we want from energy storage. So science works sometime. Let's see it again. Oops, sorry. Shining light, these are the supercapacitors. We shine light, so we charge the supercapacitor. After shining light for 10 minutes, we connect the lamp to the supercapacitor. So this is going to be our power source, just like a computer or a cell phone. And our supercapacitor charges or uses its energy to light emitting diode. So it's not commercial yet, of course, but it's a nice concept. And maybe one day we can have supercapacitors on a roof that are containing carbon dots, and they will be induced by light, and I will be very rich, maybe. Thank you. We need to charge them.
When you increase the concentration of carbon dioxide, then the efficiency will increase. But sir, you have that shown the graph, that's showing that when we increase to two decreasing that one.
First of all, I think you are a very good observation. it means that you really listen to the lecture, which is very good. That's true. When we look at this graph, we see 0, it's not so good. Then half milligram better, 1 milligram is better. 2 milligram is not so good. You know why? Because when you have so many carbon dots, it's getting crowded. Just like people in a crowded room. If you have too many carbon dots, it's very hard for them to move, and then they're not good electrolytes. That's the reason why you don't want too many carbon dots. You need enough carbon dots to be able to move freely from the anode to the cathode.
First of all, sir, thank you for the prior discussion. So my question is that, not related to the concept, but this concept was so amazing. My question is that you have thought about all these, or you have a team along with you, sir? Because when you said, let us make the electrolytes move, and that is like a very nice concept. So, sir, this is your thought process, or?
That's a very hard question. You know, I like science. I like other things in life. But usually I think of my projects. And the way it works is that you start with something, and if you think and think and think, sometimes you have interesting ideas. This idea came because we have been working for maybe 5 or more years on supercapacitors. And we worked a lot on electrodes of supercapacitors. We made different nano-porous electrodes. So we had a lot of work on supercapacitors. Now, because we worked so many years on electrocapacitors, then I was thinking, okay, we have electrodes, but we also have electrolyte. What can we do with the electrolyte? And then, of course, you see that we did a lot of work with carbon dots. So we did 1 + 1, the photothermal effect of carbon dots, this story about supercapacitors, and then the idea came. You know, some ideas don't work. It's not everything that is working. But sometimes things work. If they give you money to do these experiments, then you can do many things.
Thank you, sir, for your nice and very interesting lecture and the topic you have covered. One of my queries is that I have heard mostly the liquid electrolyte, right? But is there something like solid electrolyte?
Actually, for practical applications, people like solid electrolytes better. Because liquid electrolyte, you know, if you have some cracks, it can go leak. So the field is actually moving to solid electrolytes. Even in solid electrolyte, you can have mobility. It's more challenging, but it is okay, it's practical. This specific system that you saw, it's actually more solid electrolyte than yes. It's not completely solid, it's like a gel-like. Yes.
What's the efficiency of
You know, it's not so efficient in terms of energy density and power density. But the nice thing is the concept. And you know, 100 years ago, cars were very slow and very inefficient. Then there is engineering to make it better. Hopefully, this concept will go towards better engineering. Yes, we are working on different, not the same thing, but other similar concepts.
Where you have taken
Not rubidium, ruthenium. This is just, I told answer her that we've been working on supercapacitors for several years. And actually this ruthenium oxide electrode is some porous, very efficient porous electrode that we developed before, like 3 or 4 years ago. So basically we use the same electrode in this system. But this is not the important part. The important part here is the electrolyte. But we used a very good electrode in order to give us good power properties and energy properties.
Any question from bankers? No. Okay. One of the pictures you have shown that polymer.
So thank you for the interesting insight. So my question is, there are various synthesis methods for this. So what have been used in your work? What synthesis have you used for the carbon dots?
For the carbon dots, it's not, we can use any synthesis we want.
So what have you used to obtain carbon dots?
In this case here, it's citric acid. Citric acid and ethynylamine, I think. The important thing for us is to make carbon dot that will be hydrophilic. So to make them, if you remember before the lunch break, I described carbon dots from citric acid and from guanidinium. And this makes them very positive. So we use the same thing, similar thing here. Citric acid and some amines. I think it was ethylene diamine that gives us carbon dots that will be positively charged.
So you also talked about the matrices for electrode and electrons. So how do we know about the matrix structure?
Well, you can take something that other people made, or you could do something that you made. Now, the same thing that he was asking, we used in here a electrode of ruthenium oxide. Okay, we used a where is it? Here. We used a nickel ruthenium oxide. This is actually a very interesting electrode. You see, it has these trees, nano trees. We synthesize it in our lab, and this is a very good electrode because it gives you a very high surface area. Remember, I said it's important to have high surface area. So we have this electrode that we used from our development. But you can use in this system any electrode you like.
Good afternoon, sir. So my question is that all the polymers are not hydrophilic at low temperature. So what will happen if we take the hydrophobic polymer?
This is a very good question. You cannot take any polymer. The unique thing about this system is the polynipam polymer, which has hydrophilic phase in low temperature and hydrophobic phase in high temperature, and the transition temperature is 34 degrees. So it's really a very special system for this polymer. You cannot take any type of polymer for this application. Maybe you can find other polymers that do the same thing. Then it will be wonderful.
Regarding the same picture, at room temperature, the polymer is hydrophilic.
That's right. Yes. Well, the functionality is just the hydrophilic or hydrophobic. There's no other changes. Actually, that's what's interesting about this polymer. Because when you increase the temperature, these rings, these polymer chains, they start moving very fast until they collapse and they make this hydrophobic phase. Exactly. In there? No, there's no change. It's the same polymer. Yes, it's a structural change.
I did the work with my student on the uniform. We prepared the hydrogel with the uniform. We cross-link the uniform with the AMPS. To apply the model to methyl, one protein, some chemicals. And we observed the same thing there. This is the pH sensitive and also the temperature sensitive. So we can use that copolymer along with the another like the nanoparticle.
Okay.
After mixing the nanoparticle with that hydrogen copolymer material, and we will make the nanoparticle.
Sure.
So it will work
If it, no, it will work definitely, but the question is, how do you heat it?
we will take the help of this nanoparticle by keeping the source in presence of sunlight.
You can do this with carbon dots. You cannot do it with any type of nanoparticles. The nice thing about carbon dots is that when they absorb light, they release heat. Actually, there are other types of nanoparticles that do similar things, like gold, for example. Gold nanoparticle also absorb light in certain wavelength and release heat. So actually, you can try this with gold nanoparticles. I don't know. You have to check.
We can use the nanocomposite also.
Exactly, yeah. You should do it. It's very interesting. Yeah.
Because we get the same result.
Mm-hmm.
In the laboratory scale, we are giving the temperature by heating.
Yeah.
So is the temperature sensitivity.
Sure. So, sounds beautiful. You should try it.
Thank you very much for that very insightful talk. So just one curiosity, did you investigate the effect of pH on the binding and detachment of this carbon dot to the polymer? Because the beta potential of carbon dot is highly dependent on the pH of the solution. Right?
That's right. Part of the optimization of the system was actually selecting the correct pH, or selecting the pH that will give you the best results. So absolutely, you're right. The pH has a strong effect on the surface charge of the carbon dots and how they are behaving in the system.
We have to maintain that pH. Should be a
Yeah,
buffer.
and we can do it with buffer, sure.
Thank you.
Is there anyone else? No. Okay. Thank you so much, sir, for giving insight.
Sure.
Information.